podcast is brought to you by LMU Munich.
I'm very happy to be lecturing at this school. Looks like it's a broad set of students. And I was told that many students have varying backgrounds, so I will try to start from bottom up and try to tell you why this problem of quantum black holes is interesting and why so many people are spending so much time on it. Can everybody see this? So basically, in recent years, there has been a lot of progress in understanding the thermodynamic properties of black hole, even going beyond the large charge limit and try to compute even finite size effects. And this leads to highly non-trivial agreements between the thermodynamic side of black holes and the quantum side of black holes. So the first part of my talk will be basically, these lectures will be talking about the semi-classical black holes, which will be related to the thermodynamics of black holes. And this is completely general. It does not require you to commit to any particular theory of quantum gravity. This follows just from rules of quantum mechanics and general relativity. But this poses, as I will explain, a lot of very deep and important puzzles, and the resolution of which is absolutely essential if you want to have a consistent theory that combines general relativity with quantum mechanics. And that's what leads us to discuss quantum black holes, which is, you can think of as a statistical mechanical side of things. So this is a bit like how the 19th century physicists proceeded, that used, for example, Maxwell and Boltzmann, you studied some properties of molecules in this room just by measuring the temperature, the entropy. At that time, they were not even sure whether the world is actually atomic in nature. But if you postulate that the world is made up of little molecules, then you can calculate the number of ways. For example, if you have n molecules and you have to put them as some typical wavelength lambda, thermal wavelength lambda, then the room in this there are so many boxes, and you have to put n molecules in that. So it gives you sort of the number of ways you can do it as that very simple formula. This is a very trivial calculation. But as you know, this is one of the most important successes of the kinetic theory of gases. This is the famous calculation of Maxwell, that then you compute the logarithm of this dn, and you find that you can relate it to the entropy. Which you can measure thermodynamically. You just heat this gas, add some delta Q over delta T at some fixed temperature T, and that tells you the change in entropy. So this very simple calculation, lambda of course depends on the temperature, as you know, is the thermal wavelength. So you must have done this calculation in courses in statistical mechanics. And this very simple computation is how you could learn about the quantum structure of matter even without having a microscope. I mean, we cannot actually see the molecules in this room, but we can still conclude about some properties of the molecules in this room. And somehow the approach that we are sort of forced to follow when we are studying the quantum aspects of gravity, and one of the leading candidates for that is string theory. Since we don't have a large hadron collider which can go up to Planck scale, we are forced to sort of rely on indirect methods, much the same way that Maxwell and Boltzmann were forced to rely upon indirect methods to learn about the quantum structure of space-time, if you like, the quantum structure of gravity by some indirect but robust arguments based on thermodynamics. So that's going to be the philosophy. And the black holes play a very important role in this story, because black holes, as you must have heard in some of the talks earlier, have this wonderful thermodynamic properties which are totally universal. So black holes, as you know, is some kind of an object whose gravity is so strong that even light cannot escape it. This is, of course, what you have heard in. And this is what we want to make precise in today's lecture, that these kind of heuristic notions we want to make precise by really studying the metric of the black hole. But the basic idea is that this black hole, in classical general relativity, is something from which light cannot escape, is gravity. And therefore, it really looks like, in classically, it's like a black body with zero temperature. It absorbs everything and nothing can come out. But semi-classically, the moment you turn on a bit of quantum mechanics, it looks like a black body at some finite temperature. And what is remarkable is that this finite temperature is related to the parameters of black hole by a very universal formula. The temperature turns out to be related to h bar kappa, where kappa is the surface gravity, which is roughly like the acceleration at the horizon, as we will explain. So, and this implies that the black hole must have entropy. By the first law of thermodynamics, because basically it has mass, so del m is equal to T ds. So if it has temperature and it has mass, then you can figure out entropy. Sorry, it must have some entropy if it has temperature. And then, so in fact, the history of black holes started with a very simple-minded question asked by Bekenstein. And it's a kind of a series of paradoxes that you have to. So Bekenstein, who was then a graduate student, asked this very simple-minded but very incisive question, that if a black hole classically, if you throw something, nothing can come out, then what if you throw a bucket of hot water into the black hole? Then it would look like that the entropy, classical black holes, can violate second law of thermodynamics. By reducing entropy. Now that's bizarre. You don't want the second law of thermodynamics is a very well tested principle. But of course, we know that when you throw a bucket of water into the black hole, you don't violate first law of thermodynamics. Energy is conserved. And why is that? Because black hole has mass. So the mass of the black hole goes up when you throw in some matter into it in such a way that the total mass at infinity does not change. So that led him to propose that maybe black hole also has entropy. He proposed that the black hole must, if it has black hole has entropy which is proportional to the area of the black hole, which is roughly the area of this region is called the event horizon. We are going to discuss this in detail. So it's like a sphere of some radius sitting here, and whose Bekenstein proposed that it must have entropy proportional to the area. But that raises another problem, that if it has entropy proportional to area, then as I said, from the first law of thermodynamics, it has mass and it has entropy. So this implies it must have temperature. From the first law. But this is inconsistent because this is inconsistent with classical GR. Because there is a Stefan-Boltzmann law that anything which has temperature must radiate. So if something must radiate, something must come out. But classically, nothing can come out because light cannot escape it. So what is going on? So this, you can see that this sort of leads to a series of paradoxes. And just by thinking about the theoretical paradoxes, people have made enormous amount of progress. So if you have a good taste and if you ask good questions and just follow the logic of the physics, you can often arrive at important conclusions. And that sort of has been the history of black holes, which I have included a bit of a historical note in these notes, to give you an idea that without direct guidance from experiment, people were able to make substantial progress by just asking these kind of questions because you know thermodynamics and quantum mechanics really well. So this led Hawking to discover that quantum mechanics plus general relativity semi-classically implies temperature. So therefore, semi-classical black holes, and then he had a very consistent, beautiful story that semi-classical black holes have semi-classical black holes are consistent with laws of thermodynamics. So you can save the second law of thermodynamics because it has entropy, and you can save the first law of thermodynamics because it has temperature. And in fact, as we will describe, everything works beautifully, and you have a very nice consistent picture of the generalized laws of thermodynamics in the case of black holes. So semi-classical black holes, sorry, which one is this guy? Are beautifully consistent with thermodynamics. But that raises another problem. What about statistical mechanics? And there is also the information puzzle. That you yeah.
But if I include the inside, the region inside of that,
Yeah, but
I cannot see the violation.
yeah, but you are an asymptotic observer staying at asymptotic infinity, and you are measuring energy and entropy from far away. So if you have some objects, so either you have to treat the black hole as an object which has entropy, which is what Bekenstein did, or you have to say that as far as the outside observer is concerned, the entropy, I can reduce the entropy as much as I like. So basically that leads you to conclude that the black hole must have entropy. But there is this leads to even a deeper puzzle, because now I can take a black hole and throw some matter into it, and the thermal radiation will come out. So I can throw in Encyclopedia Britannica Volume 1 or Encyclopedia Britannica Volume 2. All the information in the encyclopedia will be lost because all that I will get is thermal radiation, which depends only on the temperature, as we saw on surface gravity. So the thermal radiation, thermal evaporation of a black hole seems to imply loss of information because quantum correlations are lost. And of course, this actually incidentally remains still an open problem, and it has not yet been resolved, despite a lot of progress in holography, and so on. This question remains open. But it requires that somehow, therefore, the black holes must have microstates. I mean, for example, in the case of the sun, when the sun, if you throw the encyclopedia into the sun, information does not get lost, and it somehow comes out later in the thermal radiation, because the sun has lots of microstates. It has all kinds of atoms inside moving this way or that way, and depending on which way the sun is excited in which microstate, the information is encoded in that microstate, and which eventually comes out in the thermal radiation if you measure some subtle correlations. So this demands that black holes must have microstates. And in general, if a black hole behaves in every respect like a thermodynamic system, we know famous relation of Boltzmann that this must be k log d, depending on some mass and charges and so on. Boltzmann relation must be satisfied. So that raises the question about what are the microstates of the black hole. And this is a problem that you cannot answer in just classical general relativity or in semi-classical general relativity, because you really need to know what makes up the black hole. And this is why this is a very, very interesting concept and very, very interesting theoretical tool for anybody like who is interested in quantum aspects of gravity, because it really is one of the very few and very precious pieces of evidence that quantum mechanics and gravity have to be combined in some consistent way. And this gives you very quantitative information about a consistency requirement about how that unification of quantum gravity has to happen. So therefore, anybody for that reason, that people who are working in quantum gravity and string theory, the black hole has turned out to be a very important theoretical tool. And this requires string theory. Of course, any other theory of quantum gravity will also do. And if you have your favorite quantum theory of gravity, the first thing you should try to do is whether it describes black hole correctly or not. And string theory surprisingly has passed a number of very non-trivial tests, and it seems to have within it the nuts and bolts to really describe a black hole as a quantum state in some Hilbert space, such that you count the number of states and that agrees with the black hole entropy. I should say a few words about string theory before I proceed. So the point is that in order to make, we have not yet been able to make contact with experiment with string theory. And the reason is that even though we believe that we somehow have some understanding of the basic equations of motion of string theory, we don't have a complete understanding. String theory exists in many phases. Or what? And in order to really compare with particle physics experiments like the LHC, we need to know precisely which phase we are in. So for example, it's like knowing the H2O molecules are described by some fundamental Lagrangian or Hamiltonian, quantum Hamiltonian, but this can exist as a water or vapor, different phases, or ice. And certain properties require you to know, for example, if you want to calculate the viscosity or something like that precisely, you would need to know whether it's in the water phase or in the vapor phase. And that's the reason we have not been able to really make contact with the experiment. I mean, this is one of the difficulties in connecting string theory with the real world. But in the absence of such a ability, what we should do is you should ask questions which do not depend on the phase. And the good thing is that the puzzles, black hole entropy and related puzzles, have a universal character. In that, if you found one phase of string theory in which information is lost, then you can just forget about string theory, because then it is leading you to pure states going to mixed states, and then you don't know. So because of this, we can therefore ask whether the black hole issues like the statistical interpretation of the entropy or the information puzzle can be addressed in some simple phase of string theory where we can actually calculate everything precisely and check whether, for example, whether this relation is satisfied or not. And in particular, in these lectures, I'm going to focus myself in a system which has a lot of supersymmetry, which is n is equal to 4 supersymmetry. And we will find that actually string theory sort of passes some of these states with flying colors. Of course, this is not to say that string theory is correct, but or whether how it's going to describe the real world or what phase of string theory is going to describe the real world. But it at least gives you some confidence that we are not just going off in some dreamland and imagining that string theory is right. But we can actually subject string theory to some really rigorous tests, even though we cannot do experiments. So it's again a bit like what 19th century physicists were doing, that if you have atomic hypothesis, you can subject it to some test by saying that, okay, let me calculate the entropy of the gas in this room, assuming it's made up of monoatomic molecules or whatever. And people were able to discover all kinds of things. For example, if you might remember Gibbs paradox, that you have to imagine that all molecules are identical. So you have to put that n factorial there. If you don't put n factorial, it doesn't agree with entropy. So you could, I mean, of course, as you know, to understand that the molecules are really identical required full quantum mechanics. You have to know spin statistics theorem and quantum field theory, really. So that took until 1940 or 1925 at least, to really understand that in what sense the molecules are indistinguishable. Whereas this work of kinetic theory was done in 1860s, almost 70 years before. So that is the kind of philosophical approach that we're going to take, that most likely string theory is not the final word on the laws of quantum gravity. But let's try to abstract from it those things that which we can be sure of and which hopefully will remain in the final theory of quantum gravity that we eventually develop. So are there any questions? So now I'm going to move to the more.
So what is exactly the rhythm you cannot describe the microspace general relativity? I mean, the propagation function is divergent, or what exactly does it?
There is no, basically that's right. I mean, you cannot really, you don't have a notion of a quantum Hilbert space. Yeah, the usual problems of general relativity being quantized, you have non-renormalizable theory. So you don't really have a framework. I mean, string theory, on the other hand, gives a framework for discussing the quantum Hilbert space of the theory, as we will describe.
Yes, but I can try, for example, calculate the propagation function.
Yeah, but then that's not renormalized. You don't, the normal rules of quantum field theory will not apply. So you don't really know how to define it. And typically when non-renormalizable theories occur, it's a signal of some missing physics, like in the case of the 4 Fermi interaction. 4 Fermi interaction was non-renormalizable. That told you that, okay, you had to have a vector boson at the weak scale. And so most physicists believe that, therefore, general relativity has to be somehow supplemented by some additional degrees of freedom. And how to add those degrees of freedom has to be consistent with this, one of these very important laws of black hole thermodynamics. And so that's how we will proceed. Of course, there are some people trying to really quantize, I mean, the loop quantum gravity approach is sort of trying to quantize general relativity, but I think it has not, as you will see in string theory now, we are actually be able to compute entropy with great detail, not just to the leading area law. And amazingly, there is an agreement between what you can compute on the left-hand side and what you can compute on the right-hand side. Okay. Okay, you can ask any questions in them while this thing is. So now what I want to do is that I want to describe black hole thermodynamics in kind of a semi-quantitative way, so that since not all of you have had courses in general relativity or quantum field theory, I cannot, and also given in just one lecture, we cannot really do it in complete detail. But I have tried to include in the notes as many details as possible, which I will not describe in the lecture, but you can refer to the notes for further details. Oh, sorry. So let's first of all try and understand what is a black hole in a more quantitative way as physics graduate students, rather than just what you would, light cannot escape it. I mean, that's okay, that's good for popular science books. So a black hole has an event horizon, and I want to sort of describe to you what is an event horizon in some more quantitative way. And the simple example is that, as you know, space-time described by a metric. I mean, space-time is some Riemannian manifold, etc. And you have a metric on it which satisfies Einstein's equations. And one of the solutions of vacuum Einstein's equations, as was described, I think, in Roberto's lecture already. So vacuum Einstein's equations have a solution. And because it's a nonlinear equation, you can actually have, without any matter present, you can have a non-trivial solution. So G is Newton's constant. So this solution many of you must have seen. So this is a two-sphere, and R is a spherical coordinate. And you have omega as theta phi, basically. Now, this appears to have a singularity, apparent singularity. And I have added an important historical note in my in these lectures that you have given. This, of course, those of you who have studied a bit of general relativity to know that this is just a coordinate singularity, not real. Just because of bad choice of coordinates. And so basically, if you make some appropriate coordinate transformation, the singularity is not there. So just some coordinate transformation that we are going to do. But you will be surprised if you, it's a really very interesting reading in history of science, that if you read, including people like Einstein, they were totally convinced that this singularity is very bad. So this, of course, as you know, describes the gravitational field outside the sun. This metric describes, this is the Schwarzschild metric. So as a metric outside a star, it's of course a very good metric. There is no matter present here. But this radius 2gm, for, let's say, for the mass of the sun, is about 3 kilometers. So if for some reason the mass of the sun was concentrated in a smaller sphere of 3 kilometers, then this singularity would really be present, because for the sun it doesn't matter, because inside the sun you cannot solve a vacuum Einstein equation. You have to put matter, whatever matter is present, and this metric is no longer valid. But then people ask the question, what happens if the sun was really collapsed to a small radius, smaller than 3 kilometers? Then you would really have to deal with this singularity. And in fact, Einstein wrote a wrong paper showing that why such singularity is inadmissible in the theory of reality and so on. And it took almost 50 years to really understand what the singularity means. So we are just going to make a very quick coordinate transformation, but don't be fooled, because oftentimes in science, the road to the final theory is actually very complicated, and people make all kinds of wrong steps, and eventually they figure out what is the right thing. So what is going to be a very simple coordinate change took a lot of struggle, and then there was a Chandrasekhar limit. Chandrasekhar showed that a star can collapse if it's big enough, and then Oppenheimer, Schneider showed that, okay, with neutrons also, basically they found that eventually when the thermonuclear fuel is finished, the star will collapse. So if a star can collapse, it will of course pass beyond the Schwarzschild radius. This is the Schwarzschild radius. The black hole radius, our black hole, RH, our horizon. So if the sun can collapse below RH, then of course you have to deal with this, and then it becomes important for us to figure out what is the nature of this singularity. And now we are not going to spend 50 years understanding this. We can just do it in 2 lines. Just try to examine the physics near the r is equal to 2 gm. So we introduce a coordinate psi, and we take the limit r going to 2 gm. Then of course it's easy to see that this metric, so only the first order term will survive of order psi. So therefore ds square becomes equal to minus psi 2 gm dt square plus 2 gm psi d psi square. And then plus terms of order 1 upon 2 gm. So you basically write r minus 2 gm as psi, and you expand in psi, and you drop terms which are down by. So it's an expansion. So if you're sufficiently close, you can drop terms of the order of psi square, whatever, psi square. This is pronounced as psi, no, yeah, psi. Now, so this is a metric that you get. And basically this factor, this is some S2 of radius r Schwarzschild. So it's just kind of a Schwarzschild sphere of radius, Schwarzschild radius. So we can just focus on this part of the metric. And it's easy to see that this part of the metric is in fact nothing but flat Minkowski space in 1 plus 1 dimension, written in funny coordinates. So therefore, obviously, since it's flat space, the sphere is of course big. So So to display this, you just introduce new coordinates. Rho square is equal to 8 gm psi, and basically you are defining it in such a way that this term, the second term, becomes d psi square 2 gm upon psi becomes is equal to d rho square. So you just solve this differential equation. I mean, just solve this, just integrate this on both sides, taking the square root, and you get this. And then the metric looks like that. So I'm just looking at the 1 plus 1 dimensional metric. And this is what is called the Rindler metric. Where kappa is equal to so this is one way to figure out what is the surface gravity. And intuitively you can think of it as basically Newtonian acceleration, if you had a star of radius 2gm, so you have if you had some object of radius 2gm, then gm upon r square would be the acceleration just by dimension analysis. So the acceleration will have dimensions of gm upon r square, and if r is equal to 2gm, this is equal to 1 upon 4gm. Of course, this is too heuristic. In general relativity, you can't use it like that, but it gives you an idea that as an order of magnitude, this is basically has units of acceleration. So it's the surface gravity at the horizon. And this is Rindler metric, which is basically Minkowski in funny coordinates. And instead of working it one way, I'm going to work it the other way. And I'm just going to start with your favorite Minkowski metric. Change coordinates. So that ds square is equal to minus du dv. These are just the light cone coordinates. And then I'm going to introduce new coordinates. This is equal to 1 upon kappa e to the kappa u, and v is equal to minus 1 upon kappa e to the minus kappa v. I'm going to introduce. So u and v, as you can see, these are the new coordinates. And in this, the metric takes the form. It's very straightforward. Okay? And then I write u is equal to t plus x, v is equal to t minus x. And the coordinate rho that I introduced there, this rho, is related to rho is equal to 1 upon kappa e to the kappa x. Then you will find that ds square is equal to e to the 2 kappa x minus dt square plus dx square, which is equal to minus rho square kappa square d rho square, sorry, dt square plus d rho square. So very simple change of coordinates takes you from Minkowski space to the Rindler metric. And therefore, a black hole very near the horizon is like a Minkowski space. There is nothing special happening at the black hole. And that's very funny, it looks like. Sorry. It's a bit of a This is going way too high. Okay, so now we have seen that the Rindler metric, which has gone, okay, it's here. Well, I mean, intellectual opposition to new ideas, whatever. I mean, it's difficult to get rid of your prejudices. I mean, for example, when Chandrasekhar talked about gravitational collapse, he was sort of made fun of, so much so that he left the UK and went to the Eddington, who was then a big authority in astrophysics. And Chandrasekhar was a young physicist. So it takes time to, Well, there were various reasons. First of all, the reason was that people thought that the gravitational collapse was a reason because you are considering a spherical collapse. You are using some very special if you had a slightly unspherical collapse, maybe the singularities don't form. I mean, you don't actually go collapse. So it took the singularity theorems of Hawking and Penrose to really show that gravitational collapses, singularities are very generic. No matter whether you have spherical collapse or non-spherical collapse, you'll always have. So there were all kinds of these objections, which were reasonable objections, that maybe all this you're seeing is because you're assuming spherical symmetry, and that's too, it's not generic enough, and things like that. So I think that's the reason, until singularity theorems were proven and the laws of black hole dynamics, this area theorems, etc., were understood. Only then, and also there was no evidence for black holes. I mean, evidence for black holes is only very recent. So why imagine something so exotic? And of course, for Einstein, it was clear it sort of almost showed that his theory is incomplete. So he obviously had a stake in the matter, and so he somehow wanted to rule out any singularities which would render his theory incomplete. So, yeah, so these are sort of, it's a question of a sociology of science.
If I write the metric was flat system in a different coordinate, I see that there can be notion of temperature for the flat system.
Yes.
So does that mean that I also have entropy for that?
You don't have, because there is no asymptotic observer. But that's actually a very, this goes to what is called the Unruh effect, and we won't have. I will comment upon it in a moment. But let's just look at these coordinate transformations first. This coordinate transformation tell you okay, sorry, bad idea. If you plot this, what is happening, the reason there is a coordinate singularity is because u and v go from minus infinity to infinity. Whereas you can see, because of the exponential map, u really goes from 0 to infinity, and v goes from minus infinity to 0. So if you plot the Minkowski space, which is like that, so this is your t coordinate. So t increases this way, x increases that way. Then I think u is equal to constant is what? U equal to constant. V equal to constant is this way. So is this way. So v increases this way. Sorry, u increases this way and v increases that way. Okay, you know what I mean. And what is happening is that u minus small u minus infinity is here, or small v minus infinity is here, v is equal to 0 is here, u is equal to 0 is here, u is equal to infinity is here. So you can see that the uv coordinates are singular, cover only part of space time. In fact, you can make a conformal transformation. For example, you can define like sigma plus is equal to tan sigma plus is equal to u or something like that, and tan sigma minus is equal to v, such that du dv gets mapped d sigma plus d sigma minus divided by cos square sigma plus cos square sigma minus. And if you forget about this conformal factor, you can basically, this is called a Penrose diagram. You can just squeeze this infinite space just to display the causal structure into a diamond. So this is u is equal to 0, u is equal to minus infinity, u is equal to minus infinity, u is equal to infinity. Sorry, this is v is equal to infinity. but V is equal to 0. And this is U is equal to the other way around, I think. Have I got it right? Sorry. Something wrong I've done here. Is it? Maybe you're right. Let's just see. So U goes from 0 to infinity, capital U goes from 0 to infinity, when small u goes from minus infinity to infinity. So this goes from minus infinity to infinity, when u goes to 0 to infinity. This of course goes from minus infinity to infinity, but then capital V goes from minus infinity to 0. Okay? So this is called a Penrose diagram. The Penrose diagram is just conformal map of the metric. So you basically forget about the scale factor. If you forget about the scale factor, then sigma plus and minus go from minus pi to plus pi. So you can sort of map it to minus pi to plus pi. But because it's a conformal map, light rays go at still go at 45 degrees. So this means that the causal structure is preserved. This is like in 2 dimensions. You are familiar that if you make a holomorphic map of a z coordinate, it's a conformal map. It doesn't change the angles, it changes the distances. The advantage is that now I can display this infinite space just on a finite diagram, and that's called a Penrose diagram. So it's just a conformal map of your original space-time. But now you can very clearly see the causal structure. The causal structure is that u equal to minus infinity to plus infinity covers only this particular quadrangle. And the full Minkowski space actually requires this entire 4 other quadrangles, altogether 4 quadrangles of this type. And this is called the Rindler wedge, or this is called the Rindler quadrangle. Now, a similar thing you can do for a black hole. For that metric, and what we will find is that let me write here. So this implies that if you started by mistake, UV coordinates, then you must extend your coordinate system. So make a change of variable so that everything can be displayed in one diagram, in one coordinate frame to UV to see the whole space-time. And the reason for that is clear, that if you had a light ray going in the first quadrangle, you'll find that after u has gone from minus infinity to plus infinity, infinite coordinate time has passed, but the light ray has gone out of your space-time. So that means it looks like your space-time is not complete. So this is called, you have to make the space-time complete, and this is called an extension of the space-time. This is, you just basically analytically make an analytic continuation is an extension of the coordinate frame. And a similar extension for of the coordinate frame for the black hole is very easy to do, and that's given by the Kruskal extension. The Kruskal extension is simply, so just like for the Minkowski observer, you have to use capital U, capital V coordinates, and for the Rindler and go from Rindler coordinates to Minkowski coordinate. It's just your bad luck that you started out solving Einstein's equation in the Schwarzschild coordinate. You should have solved them in a better coordinate frame. And those coordinates are called the Kruskal coordinates. So once again, you can see that somebody's name is associated with this coordinate frame, coordinate change. So it's not, once again, as trivial as it now appears. So if you define what is called a tortoise coordinate, r star is equal to r plus 2gm log of r minus 2gm divided by 2gm. The reason for doing this particular coordinate frame is that then you get a conformally flat space-time. You can just write this as 2gm upon r minus dt square plus dr star square. And it's easy to see that near the horizon, you can check, because this factor will give you r minus 2gm, this zeta, which you exponentiate. So near horizon, r star behaves like the x coordinate above. And t behaves like the t coordinate, the small t coordinate. So it's clear now, therefore you have to go to capital T and capital R or capital X coordinates, or capital U and capital V, and that's called the Kruskal extension. So you can define U is equal to T plus R star. Do I have plus or minus? T plus R star, and V is equal to T minus R star, etc. And then define, you can write this as minus 2gm upon r e to the minus r upon 2gm du dv, which is equal to sort of e to the minus u minus v divided times kappa du dv. So exactly like the Schwarzschild coordinates, you can see that when r is equal to 2gm, this factor is not important. And it looks like, I mean, this factor is 1, and this factor looks like your, that factor, this factor, e to the kappa x. So this is called the Kruskal extension. And if you plot the Kruskal extension, it looks like that. R is equal to 0 has gone inside. R is equal to 2gm looks like that. There is a singularity in the past which we will not worry about. This is R is equal to 0. But if you plot, if you now make a Penrose diagram of it, it looks like that. And observers, Schwarzschild observers, who are basically now, what has happened? If you are staying far away from the black hole at some fixed radius, you are just going happily along on a straight line. But as you, there is a black hole here at r is equal to 2gm. As you start, if you want to now stay fixed, let's say, so let's say that for the sun, the black hole radius is 3 kilometers. When you are at 300 kilometers, you don't even feel the gravity of the sun, it's just sitting there. But as you start going closer and closer, the gravitational pull will become more and more significant. And if you want to stay at fixed radius, you will have to accelerate at uniform acceleration. You will have to turn on your rockets. And as you come closer and closer, the amount of acceleration, proper acceleration that you require becomes more and more. And in fact, if you really want to stay fixed at r is equal to 2gm, in fact, you will have to have infinite acceleration and travel at the speed of light. And that is the essential property of what is called the event horizon. So now, with this machinery, we can state precisely what is a black hole. So are there any questions at this point?
I didn't get the point that if I see from the
Yeah.
Will I compute the same thing that
You will not, because, so that's an important difference between the Rindler coordinates and the black hole coordinates, is that, see, the Rindler coordinates are valid only near the horizon. So the black hole looks like flat space only near the horizon. Far away from the horizon, it's not like that. So because of the fact that, you have this 1 upon r, it goes to flat space. So this coordinate system looks different. So you should not take black hole to be Rindler everywhere. It's only near the horizon that the black hole looks like Rindler. But I wanted to motivate the parameters, because all the thermodynamic properties really come from the near horizon properties of the black hole. So that's why to focus on the near horizon geometry, I made this coordinate change, and I motivated that near horizon it looks like this Rindler observer. And we will discuss this in the tutorial. The Rindler coordinates are suitable. So let me now erase this. Just a second. Yeah, please. At r equal to 0? In the Rindler coordinates, you're right. In the Rindler coordinates, the coordinate system is bad at infinity. But so that's I think also related to your confusion. That in the Rindler coordinates are good for describing the physics near the horizon, but they are bad at infinity. But these Kruskal coordinates are well behaved also at infinity because of this factor that 1 upon r. It's not just flat space. The point is that as you start going away from the horizon, you start seeing the effects which are down by 1 upon r. See, we approximated the black hole geometry near the horizon, ignoring terms which are 1 upon r. If you start including the terms which are 1 upon r, you'll find that the Kruskal coordinate frame is well behaved even at infinity, and it becomes flat because it's clear. You see, at infinity, okay, this maybe we will discuss in the tutorials if this confusion remains, but the main point that I want you to focus on for now is that the Rindler coordinates with constant acceleration in flat space, in Minkowski space. So you have this Minkowski space, and if you have an observer who is moving at constant acceleration, then what happens is that suppose that observer, she's coming at the speed of light, but the acceleration slows her down, eventually she comes to a stop. Suppose the acceleration is this direction. She's coming at the speed of light, because of the acceleration it eventually stops, and then she gets accelerated and goes, because you have constant acceleration, so you keep on increasing your speed. So if you have the rockets turned on all the time at fixed constant acceleration, and you start with some big speed coming this way and the acceleration is that way, you'll come to a stop and then go off. So this is a hyperbolic trajectory. And these are precisely the trajectory of x is equal to constant, or r is equal to constant trajectories. So r is equal to constant from the black hole. The main confusion why it took so many years to understand the black hole was r is equal to constant when you are far away looks like somebody who is a freely falling observer. There is no, you don't need to turn on your rockets. You just stand here, gravitational force is very weak, the sun is over there, and you just stay. If you just stay here, you will stay at constant radius. But as you start going closer to the sun, you have to keep on accelerating, otherwise you'll fall into the sun. And you have to maintain constant acceleration if you want to stay at the fixed radius. And that acceleration means that you're coming at infinite speed, your trajectory is like that really. And as you go closer and closer, you're basically coming at the speed of light, getting stopped here and going off at the speed of light. And that's why it's a very singular, this place is a very singular place. And if you look at the constant t slices, these look like the constant t slices. And you notice something very interesting, that the constant t slices tell you that as t is increasing, you're going forward in time, in the real time. Capital T is increasing. So your t is your time, is the real time. But look at here. So suppose this was t is equal to minus 100 and this was t is equal to plus 100. So as you go from minus 100 to plus 100, you're sort of moving forward in time. This is your future direction. This is your future. But in here, if you go from minus 100 to plus 100, you think that your coordinate time is increasing, but actually you're going backward in time. And this mismatch between what is forward in time in real future direction and what is forward according to the coordinate time is what is responsible for Hawking radiation. And a very intuitive idea to think about the Hawking radiation is that if you have a quantum fluctuation like that, which we know a quantum fluctuation in Minkowski looks like particle production. For Rindler observer. Just a second. Huh? And this is the so-called Unruh effect. That even in flat space, if you try to do quantum field theory in flat space carefully, what you find is that two observers don't agree. The notion of a particle is not well defined in quantum field theory. The notion of a local field is well defined, but notion of a particle is not well defined. As you can see here, your time is going from minus infinity to plus infinity. So the Minkowski observer says, well, a quantum fluctuation occurred, a particle-antiparticle pair was created, and they got annihilated. All the time here in this room, as we know, there is quantum fluctuation happening. This is the 0-point energy. But this observer thinks that, okay, the particle got created at t is equal to minus infinity, and then it lived forever, because in his coordinate time, this is t is equal to plus infinity. So from minus infinity to plus infinity, this quantum fluctuation lived forever, and therefore the Rindler observer concludes that there is actually particle production. And this very heuristic reasoning you can make very precise using quantum field theory in quantization of field theory in curved backgrounds. So this actually I will refer you to, there's a nice book of Birrell and Davis. Okay, sorry, there was a question. Okay, very good. So now, this is sort of a heuristic derivation of, oh sorry, I don't want to do this. Yes. Yes, yes. How do we do that? I'm going to do that in a moment. So now we want to derive the notion of the precise relation between Hawking temperature and kappa. And a real derivation actually would require almost 3 or 4 lectures. But we are going to follow a shortcut, and I think Roberto has already used it a bit. And the basic idea is that if you are doing statistical mechanics, with some Hamiltonian in quantum mechanics. We know that you can write this as a functional integral, or in fact, yeah, you can write this as phi in some complete basis. I can write this as whereas phi is a complete basis. Just think of a one coordinate quantum mechanics, but you can generalize it to field theory very easily. And this we know can be written as a functional integral I am assuming that you have done functional integrals, but basically the point is that the functional integral is going at some phi and is summing over paths, starting at phi and coming back at phi, and for each path you calculate a c of phi for each path. So each path is phi of tau, such that phi of 0 is equal to your, let's call it phi naught, and phi of tau e is also phi naught. So basically this is sum over paths, starting and ending at phi naught. Basically weighted by the Euclidean action. So if you haven't seen functional integrals, this is the quick summary of the functional integrals, that you are just weighting. You take a path, you compute the classical Euclidean action on that, and you sum over all paths with this weight. It's a probabilistic computation. And basically we see that this gives us a relation between periodicity and Euclidean time, and this is Euclidean time. You see, if you had Lorentzian time, then that time evolution matrix is IH, some Lorentzian time divided by h bar. This is your time evolution matrix. So this is Euclidean time because we have put t is equal to minus I Euclidean to go from here to there. So we see that there is a relation between periodicity in Euclidean time so let me call this actually capital TE, because this is the total time that you are taking, and this is a trajectory of TE. So tau E is going from 0 to TE. Periodicity in Euclidean time, which is TE, is related to inverse temperature beta h bar. And there is a more formal, there is what are called the KAMS Kolmogorov-Martin-Schwinger relations. You can, there is a more formal way of stating this whole thing, but basically if you notice periodicity in Euclidean time, you can interpret that as a signature of thermality. So is this clear? So you can see that a quantum mechanical system which is at some inverse temperature beta can be mapped to Euclidean propagation of the particle with a periodicity in the Euclidean time. If this is periodic, the field phi of TE is equal to phi of 0. So you are summing over in the field space, you are summing over fields which are periodic in the Euclidean time. This is one quick way of determining what is the inverse temperature. Now let us look at the Rindler metric or the black hole metric. Yeah, in the Euclidean case, you get minus the Euclidean action phi. If you were doing a real time, you would have gotten e to the is. So that's the only difference. Otherwise, you can write it. So in Euclidean time, you just think of it as a Brownian motion. The particle is getting kicked around, and it goes there. Think of a Brownian particle in some fluid, and then you are summing over paths because you have some probability. Suppose it was a random walk, then you have some probability which is given by the action, and you just sum over the total probability of finding the particle starting here and there is the sum over all probabilities. So just a regular law of adding probabilities for a random walk. Yeah, so in Euclidean time, think of a Brownian motion. That's also basically, as you know, the Schrodinger equation goes to diffusion equation. Schrodinger equation is linear in time, and the diffusion equation is linear in time, but this I h bar del by del t becomes just del by del tau. So the diffusive process looks like quantum propagation if you do. Any other question? So basically, therefore, by looking at the metric and its periodicity, so given this metric, so incidentally this makes it clear, why this is a coordinate singularity. You can see that the t coordinates are bad. At the origin. Because they are sort of going this way, you can see that there is a singularity here. This coordinate frame is singular because, let's try to understand what do we mean by coordinate singularity a little better. If we make Euclidean continuation t is equal to minus I tau, then the Euclidean Rindler metric just becomes rho square kappa square d tau e square plus d rho square. But this you recognize immediately as polar coordinates. Rho square d theta square plus d rho square, where theta is equal to kappa times tau e, and the rho theta coordinate, the polar coordinates as you know are singular at the origin. And we should use Cartesian coordinates. So do you know why rho theta coordinates are bad at the origin? So why are these coordinates good? And these coordinates are bad. What? No, but suppose theta has periodicity, so theta has periodicity 0 to 2 pi. No, there is no conical singularity. It's not that there is the space is singular, the coordinates are singular. Why are the coordinates singular? Because x is equal to 0 and y equal to 0. When are coordinates good? Coordinates are good if given a point, you can associate with it unique coordinates. Otherwise, the coordinates are not good. Right? If given a point, if I can associate 3 coordinates, 3 different numbers, then your coordinatization is not unique. So Cartesian coordinate is unique because it's nice because this point is on this grid is 3, 4. And this point is 0, 0. It's unique. Whereas here 0, 0 corresponds to rho equal to 0 and theta anything. Because as long as, recall, x is equal to rho sine theta and y is equal to rho cos theta, whatever, cos theta, sine theta. So once rho is 0, x and y is 0, independent of the value of theta. So it's the same way Schwarzschild coordinates, Schwarzschild are bad. Similarly, Rendler are bad, or bad coordinates, but Kruskal coordinates are good. And which is like the Cartesian coordinates, roughly speaking. Is this clear? So now we understand very precisely what was the problem of the coordinate singularity of the Schwarzschild black hole. That you simply chose, in Euclidean section is it's very closely related to the polar coordinates. Simply that there is nothing wrong, of course, as we know, this is just flat space. There is no singularity at the origin. Right? Rho equal to 0, there is no singularity. It looks very, very singular. Rho going to 0, your metric, one component of the metric is going to 0. Exactly like what happens for the Schwarzschild black hole. But that's not a real singularity, precisely because you have more than one coordinates corresponding to a single point. And once we see this, we immediately recognize that the periodicity in Euclidean time, so this implies that beta h bar is equal to h bar divided by the temperature of the black hole is equal to 2 pi divided by kappa, because tau e is, so therefore tau e goes from so this implies this famous relation of Hawking that the black hole has temperature, which is h bar kappa divided by 2 pi. So are there any questions at this point?
Is there any procedure to find out coordinates are bad or something?
Huh?
Let's say I start with some coordinates. How do I find out if it's just a coordinate singularity or
Yeah, so it's not always easy. You have to figure out. First thing you'll try to do is try to compute the Riemann tensor and check whether the tensor is, for example, in this coordinate. You try to calculate the Riemann tensor, Riemann curvature, and see if there is a curvature singularity. If there is a curvature singularity, then you say, okay, then life is bad. If you don't find a curvature r mu nu equal to 0, that does not mean that there is no singularity. It may be that some very high derivative, covariant derivative of Riemann tensor is 0 or is divergent. But so you have to proceed really, and what I have shown you is perhaps the shortest path to finding this is the best way to suppose, and this will be one of the exercises in the tutorial, that you take now a more general black hole, Reisner-Nordstrom black hole which has charge. You can run this whole calculation again on that black hole, look at the near horizon geometry, figure out the surface gravity. Again you will find that it looks Rindler with some different surface gravity which depends not only on the mass. So now what we have found is that kappa, which is equal to 1 upon 4 gm, we have found a relation between the temperature and the mass. So temperature is equal to h bar 8 pi gm. Notice that this goes to 0 as h bar goes to 0. So we recover the classical black hole. The classical black hole, as we said, has 0 temperature. If the h bars had come below, then it would not have a smooth classical limit. So we should be happy that h bar is coming on top, and therefore the temperature is going to 0 as we take the classical limit. H bar going to 0 limit, you get 0 temperature, you recover classical general relativity. But otherwise, you have some temperature for the black hole determined by the parameters of the black hole. So that's the lesson I want to take in the next 10 minutes and formulate the laws of black hole. I have 10 minutes, right? Because I started 10 minutes later. No, I did, according to my watch. Okay, well, if you're hungry, we can stop. Oh, sorry. Sorry? Yes, yes. So the point is that you're right that if the Rindler observer, I mean, the Unruh effect that we discussed is really bizarre. What we are saying is that in Minkowski space, there is no funny business, something that we think we understand very well. Simply by climbing onto a rocket, I'm going to detect temperature. If my rocket is accelerating faster, I will detect higher temperature because kappa is basically the acceleration parameter. So, the higher the acceleration, higher the temperature. So, it looks like there is no observer independent notion of temperature because a person who is at rest sees no temperature. Someone who is going at the accelerated sees temperature. What is special about the black hole is that black hole has an asymptotic observer at infinity. And in fact, it's very interesting to plot. So, one observer who is special is an observer who, so there are two observers in black hole, asymptotic observer who wants to stay at rest far away from the black hole, and freely falling observer near the horizon. Now, the freely falling observer near the horizon, I mean, by principle of relativity, a freely falling observer is really what defines inertial frames. So, this is like the guy who is in the Minkowski frame. In Rindler space, we don't have the notion of asymptotic observer because Rindler space, if you look at the Rindler metric, it does not asymptote to flat space at infinity. But we know the Schwarzschild metric does go to asymptotically flat space. So, there is a difference between Rindler metric and Schwarzschild metric precisely in this way, that r going to infinity limit, you get r going to infinity, Schwarzschild becomes flat. Goes to flat space. And therefore, we can talk about the temperature seen by the asymptotic observer. This is the temperature seen by the asymptotic observer. The temperature seen by the observers, you have to actually, there is a Tolman relation that the observers who are closer and closer have to accelerate more and more. So, they actually will say higher and higher temperature. So, the temperature seen by the, if you try to go really close to the black hole and keep at fixed radius distance, then you will see actually even hotter and hotter temperature. So, this is a standard, this is basically gravitational redshift. So, you always have to account for gravitational redshift whenever you are talking about the temperature. So, when you have doing thermodynamics in general relativity, when you say that it is in thermal equilibrium, you have to take into account that after taking the gravitational redshift into account, it is in thermal equilibrium. Otherwise, obviously, because of gravitational redshift, the temperature energy here is more than the energy over there. So, in order to have thermal equilibrium, the temperature also has to be more than the temperature over there. And that's exactly the same, that if you're near the black hole, the temperature has to be higher than if you're above the black hole, far away from the black hole. But the important thing is that that temperature at infinity has a finite limit, and that becomes the h bar kappa upon 2 pi, which does not depend on where you are. And this is shown by the, if you look at the Euclidean Schwarzschild geometry, it looks like this. So, this is your flat space, but it asymptotes, so this is the periodicity at infinity. Periodicity at infinity, you see that tau e is going at, what was that, 2 pi divided by kappa, 8 pi gm. So, over here, this was your rho and theta coordinates, if you like. This was your polar coordinate frame. So here it looks like just a flat plane. This was the rho theta. But as you go out, you have to remember you have to use this tortoise coordinates. So what actually you find is that you don't get, whereas in Minkowski space what will happen is that the periodicity at infinity will go to 0. If you had taken the Rindler space and did the continuation, it would look like this, but then it would just go on like that. So this is your Rindler space. So as a result, the temperature seen at infinity is 0. Whereas here, your geometry sort of becomes cylindrical at infinity, and therefore the temperature seen at infinity. So this is really like something in a thermal bath here. So you really see a thermal bath far away from infinity. Whereas for a Rindler spacetime, if you did not have this factor at r going to infinity, you would see 0 temperature at infinity. So is this clear? I think that also probably answers your question, but this we can discuss a little bit more detail in. Okay, in the remaining 5 minutes, let me just summarize what I want to say. The general lessons for black holes. So we have seen that a black hole has an event horizon. So definition of a black hole. Basically a black hole is something which is the inside is separated from the outside, has an event horizon. Which is a stationary null surface. So I am just going to give you some definition so that this was r is equal to 2 gm. It's stationary, meaning it does not change with time, asymptotic time, because r does not change in time. R is equal to constant, is stationary, time independent, where time is the time at infinity. So del by del t is a killing vector. So those of you who know, is a killing vector of the metric, which is time-like at infinity, at asymptotic infinity. If you have a space-time which has a killing vector simply means that the metric does not depend on it. So our Schwarzschild metric clearly does not depend on time coordinate. It just it depends only on the radius, and it is time-like at infinity. So r is equal to 2 gm is clearly time independent, but it's simultaneously null. It's like a light ray. So whenever we have a surface which is simultaneously stationary and null, that's called the event horizon. And that causally separates, this is the singularity, causally separates the inside from the outside. Why does it causally separate inside from the outside? Because whatever is here cannot causally come out without traveling faster than the speed of light. So this is a more precise idea of a black hole rather than saying that the force of gravity is so strong that nothing can come out. What is actually happening is that the causal structure of space-time itself is changing, and basically constant r was basically a space-like observer here, time-like observer here. It becomes space-like. So what constant r is equal to 0 singularity is really in your future. You think of r is equal to 0 as being over there in the center of the black hole, but it's actually not at the center of the black hole. It is sometime in your future. So basically space and time change their role inside. So that's a more precise definition of a black hole, that it has an event horizon which is a stationary null surface and which causally separates inside and outside. And given this, we were able to deduce a temperature for the black hole, laws of black hole thermodynamics. It has temperature. Oops. Temperature is equal to h bar kappa upon 2 pi. And then from the first law of thermodynamics, this is described in the notes, that in classical general relativity, people were able to derive this beautiful area theorems This is the classical statement, follows from classical GR. And area always increases. So if you take two black holes and collide them, they can go into a bigger black hole because the total area increases. But a bigger black hole cannot split into two smaller black holes. So what processes are allowed and what processes are not allowed? This looks very much like the first law of thermodynamics. If you just put an h bar here and an h bar here. And this looks like entropy. So this immediately tells you that the Bekenstein-Hawking entropy of the black hole is area over 4, there is a g here actually, area over 4 g h bar. And with this, we basically bring harmony between thermodynamics and black hole physics. But now we associate entropy with the black hole, henceforth, and then the generalized second law of thermodynamics says that, as was being suggested, that you just count the total entropy of the system, including the entropy of the black hole, and then you will find that in all processes, entropy always increases. First law of thermodynamics is satisfied because the black hole has temperature. So all the paradoxes that I raised in the beginning get resolved. And look at this, this is a very beautiful and precise relation. Area is simply 4 pi r horizon square. It gives you a very deep connection between the geometry, because this is some geometric quantity, area of the horizon. Surface gravity is also some geometric quantity, periodicity at infinity in the Euclidean solution. It gives you a deep connection between geometry of space-time and thermodynamics. And something that you would not have guessed, that somehow quantum mechanics and geometry of space-time lead you to believe that there is a thermodynamic quantities are associated with the black hole. So now from next time onwards, we'll start on understanding the set. So this sort of finishes the classical, semi-classical story of black holes. And there is also the 0th law that temperature is constant. Corresponds to the fact that the surface gravity is constant on the black hole horizon. This of course is trivial for a spherically symmetric black hole, because by spherical symmetry it has to be constant, but also for spinning black holes people found where you don't have a reason by spherical symmetry that kappa has to be constant. So you really have laws of thermodynamics. The temperature is like the kappa is really like the equilibrium temperature, and the first and second law of thermodynamics are satisfied. So the next time the question we would like to start addressing is that is S is equal to k log d. So that's going to be the topic of the next 2 lectures. Okay, I think I'll stop here.